so the other day we were talking about vector component addition, and we were working on questions that were not perpendicular, okay, that we had several angled vectors that we had to find all the x's and y's for, okay, and all that kind of stuff. Now I realize that was last week, we did a lab yesterday, so it's not really fresh in your mind. So I want you to copy down question number 2. We're going to quickly walk through it, okay, so that you remember what the steps are, how we go about finding vector components and then putting them together to get our entire resultant, okay, for the question. So just have you copy down number 2, and then I'll walk through it with you. If you think you're ready to just try it on your own, then go ahead and don't wait for me, okay? But I'm going to walk through it for those of us that maybe forget or just want a quick refresher, okay? First step in any vector component addition question is that we have to draw the diagram, right? Now, if I'm looking at these two vectors, like one's north of east, the other's west of north, like it's almost a complete backtrack. So in a question like this, and in all questions, scale is important, okay? If I don't draw the arrows, okay, with lengths representing their lengths, and I don't get the angles right, my diagram might lie to me, right? And the problem with that is this: if I draw the diagram wrong, I'll do the math right. But when I get the answer, my answer won't agree with my picture. Human nature says we're going to doubt which part of what we did, the picture or the math.
Math.
Yeah, which is crazy because the math is actually the most consistent part of this. It's the picture we're most likely to get wrong, okay? But human nature is to assume that, well, come on, it's a picture. I can't screw that up, but math's hard, so I got to screw that up, okay? When in actual fact, most of the time, people make mistakes on these questions not because they do the math wrong, okay? Most of the time, the mistake is in the drawing, right? The math part is always the same. All right, so what we want to do then is get our diagram started. 15 meters at 15 degrees north of east. All right, so I'm going to start out with a reference line that is due east. I'm going to go 15 degrees north of that. All right, so it's not a very tall triangle. This is 15 meters. This is 15 degrees. Here's x and here's y. My second vector is almost the same length, but it's 5 degrees west of north. So I'm going to draw myself a reference line that's north. I'm going to make it very narrow because it's only 5 degrees. Okay, 13 meters long, 5 degrees. Here's x, here's y. Right, everybody okay with that? That means then that my resultant goes from my initial position to my final position, is hopefully straighter than I drew it. Okay? And then it also has an x, a y, and an angle. And since these are both displacement vectors, it will represent the total displacement of the soccer player. All right? Everybody okay with that? Mm-hmm. Now, next step is I got to find all the x's and all the y's. So I'll start out with the black triangle. Okay, black x is the adjacent side to my angle. So I'll use the cos of 15 degrees times the hypotenuse, which is 15. It's a little bit confusing. Right. So I'll have the cos of 15 times 15. So my x component is 14.489 meters. And that's east. Okay, I should have drawn those on there as well. Right. Obviously, I'm going to keep all my decimals when I do any further calculations. All right, my y component is the opposite side, so I'll be using the sine of 15 times 15. So angle times the hypotenuse. All right, so my y component for that one is 3.882 meters. And that's north. Going all right with that so far? Okay. Then I need to find the x and y components for the red triangle. On my red triangle, x is opposite my angle. So x will be calculated using the sine of the angle, 5 degrees, times the hypotenuse, which was 13. All All right, so that's going to be 1.133 meters. And that's west. And then my y component is the adjacent side, so that'll be the cos of 5 times 13. All right, so that's 12.951 meters, and that's north. Okay. Now I've got the x's and y's for the two vectors I was given. Now I can use them to find the x's and y's for the for the other one. Yeah, for the one I wasn't. It's called the resultant. That's the term, sorry, I was looking for. Okay. In this case, the resultant represents the overall displacement of these two vectors. Okay. All right, so if I want to find green x, okay, green x is going to be black x, which was 14.489. Okay, actually plus negative 1.133 or minus 1.133, whichever makes more sense to you, because they are in opposite directions. Does that make sense to everybody? Right? The first vector I went east, the second vector I went west, right? So I have to treat them that way. And I have to use all of my numbers. So 14.4888739, okay, minus 1.133024656. All right, so 13.356. 13.356. Meters, and that is east. Right, to find y, okay, I'm going to use my two y components. They're both north, so I just need to add them together. So that'll be 3.882 plus 12.951. And I'm sure I lost one of those numbers on the calculator, so I'll have to get it again. So cos of 15 times 15. All right, so my overall y component here is going to be 27, seems kind of big. As it is. Okay, something got messed up here. All right, let's just try that again. Oh, because I went cos when it should have been sine. That's why. Okay, I'm just going to get those two numbers again here, guys. So sine of 15 times 15. So this is black y, okay, plus, and then I'm going to get red y again here, cos 5 times 13. All right, so my overall north component is 16.833. Meters, and that is north. Okay, so now I've got these two sides of my triangle. Okay, this is 16.833, we said, right? Yeah. Meters going north. Okay, this one here is 13.356 meters going east. Now that I have those two sides, can I find the magnitude of the displacement?
Yeah.
Using
Pythagorean
theorem. All right, so my overall displacement will be the square root of 13.356 squared plus 16.833 squared. Okay, and of course I've lost my number again. I'm going to shortcut. You're not going to do this. Okay, 13.356 just because I want to calculate it again. okay, plus my answer squared. All right, so I'm getting that my overall displacement is 21.487, okay, or 488 meters. 21. Meters, and then I also have to find my angle. Now, I drew the triangle this way. Would it have been okay to draw it this way? Sorry. Okay. I still get the same magnitude. All I'm going to get is the complementary angle to what I'll get with my triangle. So with my triangle, x is opposite, y is adjacent. Right? So I'm going to find theta, right, by going tan to the minus 1 of 13.356 divided by 16.833. Again, you would use all the decimals because you wouldn't have screwed it up like I did, okay, and lost all of your numbers, but I'm going to be lazy. Okay, 13.356 divided by 16.833. All right, so I'm getting 38.43 degrees. 38. Degrees, and if I look at my triangle, okay, that is going to be east of north. Okay. All right, last thing I have to check. How many significant digits should my answer have? 2, 2, 2, 1. Okay, ridiculous to have 1, but that's what I've got. So, okay, and this is what I didn't want on our quiz. Okay, was to have this happen. So I have to go 2 times 10 to the 1 meters, because that's 21 to 1 significant digit, okay, at 4 times 10 to the 1, that's 40 degrees to 1 significant figure, okay, degrees east of north. Okay, I would never have you have a final answer with 1 significant digit, right? Just meaningless. You wouldn't want to do that. Okay, is that ringing a bell for everybody?
Yeah.
Okay, on how those work? All right. Then I want you guys to try number 3. Okay? I'm going to give you enough time to get way ahead of me. All right? I'll draw the diagram in a few minutes so you can check if you got the diagram right, and then I'll let you get ahead of me again. All right? So I'm going to give you some time working on number 3. Okay. So on this one, the purpose of this question is to illustrate, once again, the importance of at least having a rough scale for your diagram. Okay? The first thing this person does is goes 300 meters south. Okay? Then they go 550 meters at 75 degrees north of east. Where is my 75 measured from? East. So I'm going to go east as a reference, and I'm going to go 75 degrees north of that. That's almost all the way back, right? The 75 is close to 90. So my triangle is going to look like this. And this line here is 550 meters. Okay, again, this is where scale is important. A lot of people make this assumption. Oh, it just makes a perfect right angle triangle as it goes across. What are the odds of that? Like really, the odds of that are astronomical. Okay, I would never be that kind. It would be too easy for it to do that. Okay, so we're looking at that this, and even this is probably not long enough. Okay, 550 meters, that's quite a bit longer than 300, but I kind of ran out of room. Okay, I might adjust this actually a little bit so that that's actually even further up to better reflect the scale. So my overall resultant goes from my initial position to my final position, which is way up there. So here's y, here's x, here's my angle, here's my overall displacement, and same thing here. Here's x, here's y. Right? That's what our diagram should look like. That's a tricky one. right? That we just have to remember those conventions that we have for drawing vectors. The length of the arrow represents its length and needs to be somewhat to scale, okay? And we want to point them in the right direction. 75 degrees north of east is a very steep triangle. Okay, all right, I'm going to give you a few more minutes here to get some of the trig done before I walk through some more. Okay, so we've got, first off, for our red vector, we don't have to find x or y because it's vertical, okay? It's not a triangle, so y is 300 meters south, and x is, what's the x component for the red one? 0. It doesn't go left or right, or east or west in this case. Okay, so that one's easy. I want to calculate, though, the x and y for the green triangle now. So, okay, green x is adjacent to my 75 degree angle, so that'll be cos of 75 times 550. So, cos of 75 times 550. All right, gives me 142.350.
So you only go to 3 decimals?
No, you keep all the decimals. Okay? Keep them all until the very end, then round. Okay, at the very end. All right, I just don't have time to write them all. Yeah. Okay, and that's going to be meters, and it is east. Okay, I need to find green y as well. It'll be the sine of 75 times 550. Because it's the opposite side, so sine of 75 times 550. All right, gives me 531.259. Meters, and that's north. Okay, so that's what I've got for those. Now I can find blue y and blue x. Okay, finding blue x is easy because I only have one x component here that's not 0. Right, so however far east I went during the green vector is how far east I went in total, and that's 142.350. Right, so I don't even really have to do any math on that one. It's just already there. Okay, so 142.350 meters east. Okay. And then for the y, I go 300 meters south, then I go 531.259 meters back north, so the difference is blue y. So that'll be 231.259 meters, and that's north. Okay, everybody follow what I did there? All right, now I can find my overall displacement using Pythagorean theorem. Okay, so that'll be 142 squared plus, or 231 squared. Obviously, with all the decimals in there, I'm not going to round that off. Okay, so square root of 142.3504748 squared plus 231.2592045 squared. All right, so my overall displacement is 271.559. Meters. Okay, so that's my overall displacement. Now I need to find theta. The way I drew that triangle, x is opposite, y is adjacent. Okay, so I'm going to find theta to be 10 to the minus 1 of that 147.350 divided by 231.259. Okay, and that'll give me my angle. 142.3504748 divided by 231.2592045. Oh, I missed a number in there. Two five nine. 259.2045. Okay, sorry, missed a number. Okay, so I get an angle there of 31.6 degrees. and for me, that's east of north. Okay, all of my numbers here, I've got two significant figures, okay, in my angle that I used for calculations, which means my final answer can only have two significant figures. So my final answer will be 2.7 times 10 to the 2, okay, meters at 32 degrees east of north. Okay? How are we feeling about that? Easton, question?
Would at 50 degrees south of west be this right?
Not south of west. I would accept
Or
58.
South of east.
Not south of east. North of east. Okay? So if you drew the triangle the other way, okay, you'd have it and you'd be finding this angle here, which would be north of east, and it would be the complementary angle, 58 degrees.
I found the angle looking down. Is that not right?
No. Okay, if I find this angle, that's not telling me how to get from my initial position to my final position, right? This vector that I'm finding points this way. If I find this angle, that points the other way. It doesn't tell me how to get there, right? We obviously end up northeast of where we started. Yes? Like Easton, here's where I started, here's where I ended. That's northeast of where I started, agreed?
Yeah.
So you can't tell me I went southwest to get there, right?
Southeast.
Southeast, I didn't go southeast to get there either. I didn't go south at all. Follow me? We talked about this a couple of times already, okay? So here's what you need to do. Anytime you draw the diagram, if you don't know what angle to find, circle your initial position. Where that circle goes through your triangle is the angle you want to find. Okay, because that will point from initial position to final position. All right, because you're saying with your answer that we went south of east. We didn't. We went northeast. That's why it's not right. Okay?
Aren't they the same?
No, they're not.
One's going down, one's going up.
Okay, if I go northeast, I end up in Calgary. If I go southeast, I end up in High River. Well, actually, no, that'd be southwest. I'd end up in like
But if you went-
Mossley.
if you went southeast.
Okay.
If you went southeast
Or
of
Vulcan.
Calgary, you go to Okotoks.
But that's not the direction I went.
Yeah, you
I
probably-
started in Okotoks and went to Calgary. Okay, it's not the same thing.
Right.
Okay.
You went southeast of Calgary.
We may be southeast of Calgary, but to get to Calgary from here, I don't go southeast. Okay? All right. I want you guys, actually in your workbook package here, okay, you'll find, I want you working on the worksheet to do with vector addition, okay? So if you go into Physics 20 classwork, okay, in your kinematics workbook here, hey, sorry, looking on page. Okay, starting on at the end of page 7 here, okay, I want you working on these. They start out really easy, like the first few are collinear, okay, and then there's a few that are perpendicular, and they're still also pretty easy, okay, but by the time you get to question number, let's say like 3, okay, in the latter part of number 3, you're going to have a bunch of angled ones, right? So you can work on question number 1 here, do a few, like maybe do A, and then do like E and F or something like that, okay? And then I would say move on to question number 3, because we've done all this stuff already. So do a couple from number 1, and then move on to number 3, okay, where we're dealing with some component addition questions. You can.